So, we have started with a bank saying that RNN can solve a lot of problems. Yes, it is a wonderful network. It is able to solve a lot of interesting problems in the time series, which the normal neural net could not solve. So, it has come with a lot of promise. And when you start using the network for a longer time, you start realizing that there are some problems also in the network. And then people, when they started implementing the RNN for various problems, they started facing a lot of issues. The one is the exploding of the values, and then second one is vanishing of the values. So, that means explode means the value goes beyond a point, and then computer responds with a not a number. Vanishing means it becomes extremely small, very close to 0, but not equal to 0. When that happens, no action takes place within the neural network, because for you to really move faster in the training, you need a good gradient. If you do not have a good gradient, the training stops. So, it will go on and on and on, and it will not know what is going to happen. And then people realize that there are two inherent problems in the recurrent neural network. One is the exploding gradient, second one is the vanishing gradient. So, let us see how it occurs, right. So, since you are going to be designing the network for various purposes, we should understand these two difficulties that we would face in the design of a neural network, and that should be addressed so that we have a very smooth training process. Okay. So, for this case, let us assume this function. Okay. So, we are going to be predicting this value, and then there are layers that compute the values as you move forward, and then the error has to be computed using the back propagation. And then the values of H 5 depends on H 4, and then H 3 and H 4 depends on H 3, and H 3 depends on H 2, H 2 depends on H 1, and H 1 depends on H 0. Okay. So, this is the arrangement that you saw in the recurrent neural net as well, right. So, in the middle layer, right, this is what we saw, because they are connected. So, what happens when these things are connected in this fashion in the time series? So, we are going to be finding the error with respect to, let us say, dou H naught, right. That means, I have to find the derivative for this, 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 and so on, right, in this direction, correct. Okay. So, how do we find this? Again, we go to the chain rule and then try to find out how dou E by dou H naught can be found out, right. So, we start with dou E by dou H, right, to update the weight that connects the Y and this, and then dou H 5, since dou H 5 depends on this. So, we have this partial derivative, and then we have to get the partial derivative of dou H 4 with respect to dou H 3, and then dou H 3 with respect to this, and so on, right. So, that means, dou E phi by dou H naught is what we want to achieve, and we have used the chain rule to split this into various partial derivatives. And then if you look at this, you can just take this out, okay, and then rest you can put it in the product form, right. Dou E phi by dou H phi, this is the first one that you can take it out, and then where t equal to 1 to 5, dou H t by dou H t minus 1 is what we have received. Okay. And then if you consider for the entire state, for example, tau is going to be the total number of states that you are going to have in the neural network, then that many derivatives you have to make, and that is represented by the generalized equation of this type. Okay. So, we have a generalized equation that represents the error with respect to the first one. Okay. So, what is the problem with this? Let us see that. Okay. So, we know that this H. So, going back to where we started, right. So, we know that H t is equal to the sum of the linear combinations of W x t and U h. That is, you have the weights connecting the previous state and the current state, you do the dot product of those and then sum it with the linear combination of the weight connecting the hidden unit and the input unit. Okay. And then you take this sigma of that. Okay. Let us not worry about whether it is a hyperbolic tangent or sigmoid. Let us call it as a. When you take the derivative of this, that is dou with respect to dou h t minus 1 state, we get a diagonal. Why we get diagonals? So, it is going to be like this. Only these elements will be available, these would be 0. So, when you take the derivative of the second term, there is no second term in this with respect to t, correct. So, these values would become 0 here, the same fashion. Okay. So, you get a diagonal values, and then when you look at the values here, this dou h t by dou h t minus 1 state, it is nothing but the Jacobian matrix consisting of the derivatives of this, and then the diagonal elements will have some values and rest would be 0. Okay. So, that is why we write this as diagonal values, and then you take the u out of that, because it is going to be u into h t minus 1. When you do it with respect to this, this goes out. Okay. And when you represent it with respect to the error that we computed, so we have to write it as dou e tau by dou h tau, and then every time when you do the back propagation, this value gets multiplied. Okay. So, if we have t states or tau states, it is going to be tau minus 1. This is u tau minus 1. Okay. So, that many times you have to multiply. So, you need to make sure that the value of u is well behaved, otherwise we are going to have trouble. Okay. This is where the trouble starts for us. Okay. So, when the u gets very small, when we actually increase the depth, when you unroll it and it becomes more than 100, when you do the back propagation, the value gets smaller and smaller every time, right. And then there are, when you do this, you are also multiplying this so many number of times. So, the value of this would become extremely small for you to do any updation. Okay. And when u gets very small, we are getting into that trouble of vanishing gradient. Okay. Okay, let us take some small example and then see how it works. Okay. So, I have considered this sentence here to find out how the values really explode. Okay, so let us take this sentence. Raj entered coffee day to meet his partner Drew. Raj said, "Hi Drew," in the next few hours, and so on. And then finally, the last sentence is Raj said goodbye to his we need to find out or predict what that missing word is, right. The missing word is partner, which is in the 7th location. If you are going to be using a word based prediction, this is our 7th word, and we need to predict the 47th word, right. So, unless you understand the whole sentence, remember this, you won't be able to write partner here. Okay. So, here from this 7 to 47, okay, we have 40 U's coming into place, right. So, when the value of U, for example, when you assume that the U gets into the range of, I am just giving a small example like this. Okay. I have taken 47 here, it could be 40, but it does not matter, the value is really low there too. The value of 0.1, for example, one of the elements of U is 0.01, and then since it has seen so many states before, it is going to be U power 47, correct. So, when you take that value, it is 1.0 into e power minus 94. Okay. If when the value is 0.01, when the value is 0.5, it is going to be 7.10 into e power minus 15. See how small it becomes, right. So, this is the problem. It becomes very, very small for you to really remember anything. That is what we say, that the network forgets whatever it has learnt earlier, right. Initially we said that RNN can go up to any sequence length. Now we are finding that there is a problem with this. It is not able to remember long sequence. The value vanishes when the word that you want to predict is found somewhere very far away in the same sentence. Okay. So, this is the vanishing gradient problem for you. Okay. So, this is a very small example. Instead of really proving it mathematically that it vanishes, I have taken this example to show you this. Okay. Sometimes the value can become large, greater than 1. Remember this, okay. The values of U, V and W are totally unbounded. Okay. We do not have any boundary around those. For example, if you look at the activation functions of ST and then ZT, we always have the values between 0 and 1, right. Here it is going to be minus 1 and plus 1. So, whereas in the case of those U, V, they are not bounded by this condition, or they are not conditioned by these values. So, it is possible that the values of U becoming smaller during the back propagation, and then when it becomes extremely small, the long term remembrance is going to be gone, okay, or the long term dependency is gone. So, it only remembers short term values. So, there is nothing that the RNN forgets. It is only because of the gradient that we are moving from the last time state to the first time state, it getting smaller and smaller. Okay, so, that is the problem. It is not the problem with what we are doing in terms of the training. It is because the values that are not properly conditioned and because we do not really take care of the value of U, V and W in such a fashion, the gradient either explodes or vanishes. Okay. When the value increases beyond 1, it is easy to control. We can actually check and then bring it down to a value which is manageable, right. The problem comes only when the value becomes extremely small. Okay. So, there are mechanisms available. Clip the gradient when it exceeds certain value during the training itself. So, this is a very easy problem to solve when the gradient goes beyond a point. Vanishing gradient is our bigger problem.